This subject is quite difficult and complex to summarize. I will try to share as much as possible. Voltage stability refers to the ability of a power system to maintain steady voltages at all buses in the system after being subjected to a disturbance from a given initial operating condition. Principal causes of voltage instability are heavy load system operation conditions, long distances between generation and load, low source voltages, and insufficient reactive power compensation. The degree of a system voltage stability. The proximity to voltage instability is strongly influenced by system conditions and its characteristics such as generation system characteristics, in particular excitation systems, load characteristics, reactive power compensation devices characteristics, voltage control devices, presence of under-load tap-changing ULTC transformers, etc. A grid operator, also known as a system operator, is a key player in the energy industry, responsible for maintaining the reliable and secure operation of the electrical grid. They constantly monitor the grid's performance, ensuring it operates within its capacity, while always meeting electricity demand. Moreover, grid operators play a role in balancing and ancillary service markets to ensure demand matches supply and to guarantee system security. Grid operators are divided into transmission system operator (TSO) and distribution system operator (DSO). Moreover, grid operators play a role in balancing and ancillary service markets to ensure demand matches supply and to guarantee system security. Grid operators are divided into transmission system operator (TSO) and distribution system operator (DSO). Transmission system operator. A transmission system operator is an organization responsible for the efficient and reliable transmission of electricity from generation plants via the power grid to regional or local electricity distribution operators. Most of the utilities' transmission grids usually have voltage levels of 1,100, 750, 500, 400 or 380, 230 or 220, or 132 kV. TSOs also usually deal with power generation plants with a net generating capacity greater than 100 megawatt. Mostly vary utility to utility. Few roles and responsibilities of TSOs. Control and operate the transmission grid and transport electricity to regional or local distribution networks. Connect networks with neighboring countries and regulate cross-border electricity flows. Ensure safe, reliable, and efficient energy supply. Provide non-discriminatory access to networks for all stakeholders. Manage the networks autonomously, from electricity production to sales. Supervise system operations, upkeep, and infrastructure expansion according to regulations. Enact balancing services after markets have closed to ensure the security of energy supply at the least cost. They use balancing energy from frequency restoration reserves to ensure supply is equal to demand and to reduce the need for backup generation. Procure ancillary services to guarantee system security. These can include black start capability, restarting the grid after a blackout, frequency response, maintaining system frequency, fast reserve, providing additional energy when needed, and so on. Increasing electrical energy demand, modern lifestyles and energy usage patterns have made the world fully dependent on power systems. This instigated mandatory requirements for the operators to maintain high reliability and stability of the power system grid. However, the power system is a highly nonlinear system, which changes its operations continuously. Therefore, it is very challenging and uneconomical to make the system be stable for all disturbances. The system is usually designed to handle a single outage at a time. However, during the last decade several major blackouts were reported and all of them started with single outages. Usually, in a voltage unstable situation, the voltage magnitudes in some system buses undergo, generally monotonic, decrease in the seconds or minutes following a disturbance. When pronounced, this decrease might endanger the system integrity, mainly due to protecting devices that trip generation, transmission, or load equipment, leading eventually to a blackout in the form of a voltage collapse. Voltage collapse is defined as the process by which the sequence of events accompanying voltage instability leads to a blackout or abnormally low voltages in a significant part of the power system. Voltage instability is considered as a major threat for secure power system operation in many power systems throughout the world. Taking advantages of existing technological solutions, such as synchronized phasor measurements, powerful computational facilities, networking infrastructure and communications, in order to monitor stability conditions and control detected instability are of paramount importance. Wide area monitoring, protection, and control systems open perspectives for effective solution of this problem. You can see the roadmap for wide area voltage stability and control in this diagram. Let us see a voltage instability examples. Depending on prevailing system conditions and its characteristics, voltage instability can manifest itself in different ways. While the voltage instability caused by a smooth load increase is intuitively clear and explained by PV curves, the instability caused by system disturbances can manifest itself in short time or long time frame after disturbance. In short-term voltage instability, a voltage decrease caused by a disturbance initially decreases induction motors' torque and the motors try to recover their torque in a time frame of typically 1 second time after the disturbance. On the other hand, the long-term voltage instability is associated with load recovery mechanisms and inability of local generators to produce sufficient reactive power. In long-term voltage instability, within a few minutes, ULTC transformers try to restore their secondary voltages after some intentional time delay restore corresponding voltage-dependent load powers, while overexcitation limiters OEL restrict reactive power production from generators. Voltage instability, resulting in voltage collapse, was reported as either main cause or being an important part of the problem in many partial or complete system disruptions. Some of the reported incidents are listed in the table. Monitoring voltage stability in real time is a pressing issue for large complex power systems. Voltage stability has been a well-established area of power system research for several decades, and its theoretical aspects, underlying phenomena as well as mechanisms of instability, have been well described. Nonetheless, transmission systems may still face stressed and insecure operating conditions, which could threaten stability. The transition of power systems due to the market deregulation and renewable integration has resulted in power systems operating under dispatch schemes and power flow patterns, for which the systems had not been initially planned. This reality brings voltage stability analysis and system protection schemes against voltage collapse once again to the forefront. Online voltage instability detection systems are key components for the protection of power systems against extreme disturbances, and may be combined with response-based system protection schemes SPS for timely activating corrective actions, when voltage instability is identified without having to rely on operator response. Wide area monitoring and protection are gradually gaining ground, mainly due to the growing development and installation of PMUs that provide input to wide area monitoring systems WAMS. One of the most favorable attributes of WAMS constitute their capabilities to provide timely protection against instability, voltage instability being one of the applications. Let us discuss about what actually stability is. The tendency of power system to restore the state of equilibrium after the disturbance. Mostly concerned with the behavior of synchronous machine after a disturbance. In short, if synchronous machines can remain synchronism after disturbances, we say that system is in stable position. Power system is a highly nonlinear system. Constantly changing environment, loads, generator outputs vice versa. Subjected to a disturbance, the stability of the system depends on the initial operating condition as well as the nature of the disturbance. Voltage stability can be categorized into static voltage stability for a small disturbances and transient voltage stability for a large disturbances. Static voltage stability refers to whether a power system stays at an unstable equilibrium point, or a small disturbance, i.e., an increase in load, causes voltage collapse. For traditional power systems, static voltage stability is determined by the active power transmission and the related voltage drop on the AC transmission line. However, for high VRE penetrated power systems, its static voltage stability mechanism has changed heavily. The key change is derived by the increasing penetration of power electronics, through which AC systems integrate VRE sources. The regional distribution of VRE is unbalanced, which requires a large amount of long-distance transmission, especially HVDC transmission. The general short-circuit ratio is derived to evaluate the static voltage stability of multi- and feed direct current DC systems under constant power and constant extinction angle policies for line commutated converters LCCs. However, although generation and load characteristics contribute a lot to static voltage stability, the stability of power systems with power electronics greatly depends on the control strategies of power electronic devices and the power injected through the devices. Namely, increasing DC injections would jeopardize the voltage stability of an AC system. The mechanism of static voltage stability in AC systems dominated by power electronics would also change. In recent years, the voltage stability of LCC-based AC systems has been studied, but the influence of voltage source converters VSCs remains unclear. You can see further detailed classification of voltage stability analysis techniques in this table. An electric power system is considered to be stable when the system returns to a stable balanced state after a disturbance as told earlier. The extensive buildup of renewable energies, especially wind and solar energy, can cause transmission grids to exceed their limits, control zones be subject to higher utilization rate, and the grid be forced to transport the power over long distance lines. This is especially the case when there are certain areas in state or country which are subject to higher solar radiations or higher amount of wind energy in a specific geographical area. The outcome of such circumstances would be power transmission networks operate closer to their operational and stability limits. The extensive buildup of renewable energies, especially wind and solar energy, can cause transmission grids to exceed their limits, control zones be subject to higher utilization rate, and the grid be forced to transport the power over long distance lines. At the same time, the rise of inverter-based renewable energies, which are replacing large power plants, leads to reduction of the rotating mass instant reserve. This fundamentally changes the dynamic behavior of the power system. From grid management point of view, changes undergoing in the generation mix has changed the dynamic behavior of the system, and the increasing volatility results in higher complexity and a variety of operational situations which have to be carefully observed and controlled, in a predictive and proactive fashion. Voltage and rotor angle stability. A power system is considered unstable from voltage point of view when the physical transmission capacity of the networks has exceeded due to large amount of power transports. The electric system is then no longer able to keep the voltage within the acceptable limits. This can lead to voltage collapse, which makes the system unstable. The rotor angle stability defines the ability of the synchronous machines in the network to remain stable and synchronous after a large fault such as a three-phase short circuit happens. The instability triggered by a sudden imbalance of the angular momentum happens within a few seconds, leading to the situation of transient stability problem. Let's see transmission network situational awareness and online stability analysis tools in short. Question is, what does this mean for network management? Normally, the dynamic network stability is assessed by offline simulation tools, based on worst-case scenarios, which were performed once or twice a year as part of planning studies. Subsequently, the stability limits, including security buffers for the later use in grid management, are derived. The previously determined stability limits can lead to inefficient network operations since the worst-case consideration is too pessimistic for most of the network situations. On the other hand, increasing the thermal limits, for example by dynamic overhead power line limit rating or use of high-temperature conductors, may mean that the stability limits of the network operations become relevant by limiting the power to be transmitted. For the rotor stability analysis, in medium term, steady-state network security calculations are in specific circumstances insufficient to provide reliable analysis of the system security in critical situations. This means that new tools for assessing network stability as part of operation planning day ahead and intraday are needed, to improve situational awareness and provide support for determining and evaluating countermeasures in critical situations. How does the dynamic stability analysis work? The setup of the data model for the dynamic stability analysis is based on extending the already existing data model for the steady-state data analysis by additional dynamic data such as controller data, detailed models of the generators, high-voltage DC transmission, fax elements, etc. The analysis of the transient stability behavior primarily uses the trajectory of the rotor and voltage angles over time under various defined fault scenarios. The critical fault clearing time is a key variable for quantifying the transient rotor angle stability. The fault clearing time shall define the maximum permitted duration of a three-phase short circuit for which the system remains stable. The fault clearing time shall define the maximum permitted duration of a three-phase short circuit for which the system remains stable. Let's see types of stability. First is steady-state stability. This is when the system can handle small and gradual changes, like normal load fluctuations or voltage adjustments. The system should be able to stay in balance and not lose synchronism. Second is transient stability. This is when the system can handle large and sudden changes, like faults or switching operations. The system should be able to return to a stable state within a short time after the disturbance is cleared. Third, dynamic stability. This is when the system can handle long-lasting and complex changes, like oscillations or frequency variations. The system should be able to damp out the fluctuations and maintain stability. Now come to the role of a system operator in detecting voltage instability. This is crucial in maintaining the stability of power systems. Here are some key responsibilities. Monitoring and responding. An important function of the system operator is to monitor and respond to unusual power system events before they proceed to a point at which they cannot be controlled. Detecting conditions indicating instability. System operators can prevent some types of voltage instability if they can detect the conditions that may indicate pending voltage instability. Implementing control actions. One of the important tasks of power system operators is to assess the system stability status and predict the occurrence of instability, followed by the implementation of appropriate control actions to prevent the occurrence of instability. Using machine learning-based methods. These methods can be categorized into 5 methods and are used to assess and monitor voltage stability status of power systems. The use of pattern recognition methods in detecting voltage instability is expanding. Preventing false operations. This information can be used by the system operator to prevent any false operation of the zone distance relay interpreting the voltage instability to be a fault. Carrying out load shedding. An early indication of voltage instability also facilitates the system operator in carrying out load shedding as the remedial action for mitigating voltage collapse. In general, the response of a system operator is limited to longer-term voltage instability scenarios. Transient voltage collapse occurs too rapidly for system operator action. Let's discuss causes of voltage instability. Voltage instability in power systems can be caused by several factors, like heavy load system operation conditions. Power systems are heavily stressed due to increased loading, leading to voltage stability problems. Long distances between generation and load. The long distances between the generation source and the load can cause voltage instability. Low source voltages. Low source voltages can also contribute to voltage instability. Insufficient reactive power compensation. The inability of the power system to meet the demands for reactive power in heavily stressed systems to keep desired voltages is a major factor causing voltage instability. Induction motors. Short-term voltage instability occurs mainly due to the presence of induction motors. Speed reduction and stalling of these motors cause a sudden voltage drop. Improper locations of FACS controllers. The improper placement of flexible AC transmission system FACS controllers can lead to voltage stability problems. Poor coordination between multiple FACS controllers. Poor coordination between multiple FACS controllers can also lead to voltage instability. Voltage drop. A major factor contributing to voltage instability is the voltage drop that occurs when active and reactive power flow through inductive reactance of the transmission network. These factors can interact in complex ways, and addressing voltage instability often requires a comprehensive approach that considers all of these elements. Detecting voltage instability in power systems is a critical task to prevent blackouts and ensure reliable power supply. Here are some methods used for detecting voltage instability. Wide area measurements. A novel voltage instability detection index named Instability has been developed, which uses reactive power losses calculated from synchrophosphor measurements. This index is fast enough for real-time monitoring of voltage stability and for dispatching mitigating control actions in time. Machine learning-based methods. These methods are used to assess and monitor voltage stability status of power systems. They can be categorized into 5 methods and include pattern recognition methods. Real-time measurements. Some methods rely on real-time measurements for detecting long-term voltage instability. Load flow Jacobian. The load flow Jacobian can be an effective index to approximately assess certain types of instabilities. Voltage drop monitoring. Voltage instability often takes the form of a dramatic drop of transmission system voltages, vice versa. These methods help system operators to detect voltage instability in a timely manner and take preventive control actions to minimize operational risk. How to prevent voltage instability? Preventing voltage instability involves a combination of technical measures, system operation practices, and the use of advanced technologies. Here are some strategies. Dynamic reactive power regulation. When the power system approaches short-term voltage instability, the fast-responding dynamic reactive power regulator near the load center can improve the post-accident voltage stability level of the system and help the voltage recovery of the system. Reactive power compensation and redispatching. The most important measure to prevent long-term voltage instability is to restore the long-term stable operation equilibrium point. Measures to be taken include switching of reactive power compensation, redispatching, and load shedding. Coordinated control of on-load tap changers (OLTCs). For multi-layer power transmission and distribution systems, OLTCs should be coordinated and controlled to avoid further deterioration of voltage stability level. Secondary voltage control. When the generator has reactive power reserve, the generator terminal voltage can be increased through secondary voltage control. Placement and coordination of FACS controllers. Another important aspect. Proper placement and coordination of flexible AC transmission system FACS controllers can help prevent voltage instability. Synchronous condensers installation. Synchronous condensers can provide reactive power support, helping to maintain voltage stability. Improving load voltage reactive power characteristics. The capacity of the system to provide dynamic reactive power support and the voltage reactive power characteristics of the load are key factors to determine the voltage stability. Therefore, increasing the dynamic reactive power reserve of the system and improving the voltage reactive power characteristics of the load are main measures to improve the voltage stability. Use of capacitors. The simplest possible solution for stabilizing an unstable DC voltage is a capacitor across the output terminals. These measures aim to improve the power system voltage stability comprehensively and all around. How to measure voltage instability? Measuring voltage instability in power systems involves several steps and methods. Measurement data collection. This is the first step in voltage stability monitoring and instability detection. Measurement data pre-processing and system modeling. The collected data is pre-processed and used for system modeling. Stability degree computation and instability detection. The degree of system voltage stability is computed, which indicates the proximity to voltage instability. This computation helps in detecting instability. Use of load flow Jacobian. The load flow Jacobian can be an effective index to approximately assess certain types of instabilities. Wide area measurements. A novel voltage instability detection index named Instability has been developed, which uses reactive power losses calculated from synchrophosphor measurements. This index is fast enough for real-time monitoring of voltage stability. Real-time measurements. Some methods rely on real-time measurements for detecting long-term voltage instability. These methods help in determining how close the system is to voltage instability and are crucial for maintaining the reliability and security of power systems. Role of the system operator detecting voltage instability. An important function of the system operator is to monitor and respond to unusual power system events before the events proceed to a point at which they cannot be controlled. As a system operator, you can prevent some types of voltage instability if you can detect the conditions that may indicate pending voltage instability. In general, the response of a system operator is limited to longer-term and voltage instability scenarios. Transient voltage collapse occurs too rapidly for system operator action. Classical voltage collapse that lasts for several minutes may be impacted by a system operator's response if actions are performed quickly. The following power system events may indicate pending voltage instability. System voltage levels are unusually low. This may be due to heavy loads or heavy power transfer. Voltage levels should be continuously monitored. If a problem can be corrected before the voltages fall too far, voltage instability may be avoided. Unusual magnitudes and directions for reactive power flows. If unusually large amounts of reactive power are flowing to one area of the system, it may point to pending voltage instability in that area. Best example is August 14, 2003 blackout in the Eastern Interconnection in USA, where operators from several area utilities had noted unusually high VAR flow on tie lines. Unfortunately, the blackout occurred before appropriate action could be taken. Heavy reactive power generation at key area generators. If key area generators are at their reactive power limit, they are not available if further reactive power is required. Avoid entering a heavy load period with low dynamic reactive power reserves. ULTC adjustments fail to move the voltage. This may indicate a reactive power shortage. Responding to voltage instability. The best response to voltage instability is to prevent instability from occurring in the first place. This may not always be possible. The following methods of response are given as general guidelines. The guidelines are divided according to our three types of voltage collapse. Long-term voltage instability. Generating resources are often found in remote locations, far removed from any major load centers. Radial power systems are constructed to connect these economical generating plants to the major load centers. Hopefully, the power system designers have planned for enough dynamic reactive reserves to withstand the tremendous reactive power losses associated with heavily loaded, long radial power systems. The following precautions can be taken to prevent a long-term voltage collapse in a radial power system. Ensure that the power plants at the sending end of the power system have sufficient reactive power reserves to support the system and the loads. These dynamic reserves must meet the requirements of the heaviest possible load period for both normal and contingency conditions. Beat all available reactive power sources at the receiving end, such as shunt capacitors, should be in service and in proper working order. Shunt reactors should be out of service. See if series capacitors are available in the radial system, they should be in service. Series capacitors lower line reactance. When series capacitors are in service, the system's MAR losses decrease. If voltages are low in the transmission system, a conservative rule of thumb is to avoid the use of area ULTCs. ULTC operation can impact voltage instability in two ways. System load naturally decreases with decreasing voltage. When an ULTC operates to raise voltage, it also increases load magnitude. In addition, when ULTCs raise low side voltage, they often depress high side voltage. ULTC operation may increase the chances of a voltage collapse. As a last resort, a system operator should consider manually dropping load. If all possibilities to control the voltage instability are exhausted, it is better to drop load in a controlled manner than to let the system collapse in an uncontrolled manner. Systems may have automatic undervoltage relay schemes installed to trip load during low voltage periods. It is critical that these schemes are in operation during the voltage collapse-prone periods of the year. Classical voltage instability. Classical voltage instability follows a system disturbance. As a result of the disturbance, there is insufficient reactive power to satisfy the demands of the system and the customer load. The solution is simple: supply more reactive power where it is needed. The means to achieve this solution may be very difficult. To prevent classical voltage instability, a system operator, if time allows, can do the following. Maintain transfer limits within established guidelines. As MW transfer increases, reactive power losses escalate. If conditions are ripe for voltage instability, consider reducing system transfers to limit reactive power losses. Ensure that all available static reactive power sources, such as shunt capacitors, are in service. In addition, make sure that all shunt reactors are out of service. Ensure that sufficient dynamic reactive reserves exist to handle any probable contingency. The amount of dynamic reactive reserve is typically determined by planning and operating engineers. System operators must ensure that these minimum amounts are actually available. Ensure that the plant operators are providing all possible reactive power. This may mean redispatching generation. Generating plants in the affected area that are normally not run due to economic factors may be run to increase dynamic reactive power reserves. Shift system generation patterns to unload heavily loaded lines. This reduces reactive power losses since these losses are a function of the current squared. G. Consider blocking operation of the affected areas ULTCs to prevent further drops in transmission voltages. H. Request reactive power support from neighboring power systems. Neighboring systems can raise voltage at common buses. This may help raise voltages throughout the affected area. I. As a last resort, consider manually dropping load. Also be sure all automatic undervoltage load shedding schemes, if they exist, are in service. Transient voltage instability. Transient voltage instability is a rapid event from the perspective of a system operator. Once the process has begun, a system operator has little role in the final outcome. There is little a system operator can do to avoid induction motor-driven voltage instability. One suggestion is to ensure protective systems are in place and functioning properly. However, if instability of this type does occur, restoration can proceed quickly if the cause of the instability is quickly identified. Relationship of the types of voltage instability. The three types of voltage instability presented in this section are not independent of one another. For example, many of the events that occur during long-term voltage instability also occur during classical voltage instability. In addition, one type can progress into another. For instance, long-term voltage instability could turn into transient voltage instability as time progresses and events occur more rapidly. Figure relate the time frames for the three different types of voltage instability. Note that different characteristics of the system are involved with each type of instability. For example, to understand transient voltage instability, it is necessary to understand how induction motors behave. To understand long-term voltage instability, it is necessary to understand what is meant by a loss of load diversity.